Hello, we are Team 2 and we are going to present waves.
A wave is a disturbance traveling from one place to another through a medium that carries energy with it. Waves can divide into transverse and longitudinal. Although they both carry energy, oscillate in a mean position, and can be analyzed by the formula velocity equals frequency times lambda, they share radical differences among them. For example, transverse waves are particles moving up and down and transferring energy to the side. A clear example is the visible light. Meanwhile, longitudinal waves are particles that move in the same direction than the energy exerted by the source. Examples of these are the springs or the sound. Waves of water and earthquakes are examples of the combination of both waves.
Hello, my partner already explained what is a wave and the difference and similarities between longitudinal and transverse waves. Now, it's my turn to explain the elements of a graph. For the first elements, I'm going to explain it with a graph of time against displacement. As you can see, this graph has in the y-axis the displacement, and in the x-axis the time. First, I'm going to explain you what is amplitude. Amplitude is defined as the maximum displacement from equilibrium position. But what is equilibrium position, or also called equilibrium point? It is the position the system will take if there were no oscillations, and it was at equilibrium. So here, as you can see, if there were no oscillations, and it was at equilibrium, the equilibrium position will be the straight line of the x-axis. So as I said, the amplitude is the maximum displacement that the wave can travel from the equilibrium position So here is the maximum displacement that a wave can travel from the equilibrium position. Now, the next question could be, I know what is the maximum displacement that a wave can travel, but how long does it take you to go all the way up and all the way down? So how much time do you take to go all the way up and all the way down to complete all the cycle or period? That is the amount of time it takes an oscillating particle to complete one cycle. So it's all the way up to all the way down. That is the period, from here to here. That is the time that it's going to take to complete the cycle. It is a unit of time, and it's represented with seconds per cycle. But you can put it like seconds, the amount of seconds of time that is going to take you to complete one cycle. Now, the next question is, how many cycles am I doing per second? So it is the opposite of period, and that is frequency, and is represented with an F. So if the unit of period is seconds per cycle, and it's the opposite of frequency, frequency is going to be cycles per seconds, and that is also hertz. So an example, if I say the period is 5 seconds, the frequency is going to be 1/5 of cycles per seconds, or hertz. For the next element, I'm going to change the graph to one that is distance versus displacement. You'll know why. Here is displacement versus distance. The next question is, how quickly is the wave moving, in this case, to the right? So the question would be the velocity of the wave. Why not the speed? Because velocity is a vector, and because I said right, I'm giving a direction. So if I want the wave speed, I'm not need a direction, it's a scalar. So I'm going to remain with the concept of wave speed. In order to know this, we must know how far the wave goes after one cycle or one period. So as we learned in the last graph, the period is this, from here to here. So the distance from this point to this point is the wavelength. That is represented also with the symbol lambda. Now, we return to the wave speed. The wave speed is how long does the wave travel in a period. So the formula is wavelength over period. So is the units of the distance, in this case centimeters, but because the wavelength can be also represented by this unit, is lambda over, so wavelength is equal to lambda over period. Now, another way of explaining this is like, if we separate these two, is like saying 1 over period times lambda. And what is 1 over period? 1 over period is frequency. So wavelength also can be frequency times lambda. Finally, I will explain the last element changing to another graph. But before that, imagine that you are plotting the movement of two particles in the same graph. One is traveling faster than the other, so in a graph of time versus displacement, the particles are not going to travel the same distance at the same time. The representation will be different. So with this fact in your head, I'm going to define phase difference. It is a measure of how in step different particles are. If they are moving together, they are said to be in phase. If not, they are said to be out of phase. So I'm going to insert the other graph. So here, imagine that this in the y-axis is displacement and here is time. So this space between the two waves is going to be the phase difference, because it's the difference of the two waves that are represented in seconds. Let's say like here is 3 and here is 4 seconds. Seconds is the unit. So the phase difference is going to be 1. Phase difference is going to be 1 second. Now my partner is going to continue with explanation.
Now, what are the differences and similarities between electromagnetic waves and sound waves? Okay, even though they are both waves, electromagnetic waves and sound waves are different. There are two aspects which differentiates one of them. The first one is the velocity. The electromagnetic waves travel at a speed of 3.0 times 10 to the 8 meters over second, compared to the sound waves that travel at a speed of 343 meters over second, in the air at a temperature of 20 degrees Celsius. Now, the second one is the medium to travel. The sound waves require a medium to travel. In the most common case, it's the air, the medium. What happens is that the compression and refraction of the air particles change its own density. This is why it's possible for sound waves to transmit through the air. Electromagnetic waves require no medium to travel. This is one of the reasons they can travel through the vacuum. After all, the main and most important difference is the fact that electromagnetic waves can travel in vacuum, sound waves can. This is why there is no sound in outer space.